And now we have the last part of our discussion on impulse and momentum. We have explosions. An explosion is basically an energetic fragmentation of an object with the fragments flying or moving away from each other. You have an object, it fragments energetically, causing the fragments to fly away from each other. You have an explosion. And for explosion, conservation of momentum is very useful in determining the resulting speeds of these fragments. Conservation of momentum, initial momentum is equal to final momentum. And when we say initial momentum, that's right before the explosion. The object is just about to fragment. And final momentum, right after the explosion, the object fragments into separate pieces, and the pieces are just about to fly away from each other. So initial momentum right before the explosion, final momentum right after the explosion. You use conservation of momentum. Initial momentum is equal to final momentum. You can also use conservation of energy if you want to, but that's only if you can account for the portion of the potential energy that was released in the explosion that was converted into kinetic energy. We know that when there's explosions, there's not only the conversion of potential energy into kinetic energy, there's also the production of sound, heat, and so on. So only a portion of the potential energy gets converted into kinetic energy of the fragments or particles. If you can account for the portion of the potential energy that gets converted into kinetic energy, you can easily use conservation of energy to determine the speeds of the fragments, to analyze the system and determine the resulting speeds of the objects. When you see that the problem talks about an object exploding, it's a safe bet that you can use conservation of momentum to analyze the system unless otherwise stated by the problem. Some problems will specifically state that you use energy analysis to solve the problem. But for the most part, when you see there's explosion, use conservation of momentum. Initial momentum is equal to final momentum. So wrapping up our discussion on impulse and momentum, let's have one more example. We have sample problem number 5. A soldier drops a 0.6 kilogram grenade into a well. The grenade free falls and reaches a speed of 20 meters per second before exploding. It divides into 3 equal parts. One part flies vertically downward with a speed of 100 meters per second. A second part flies to the right with a speed of 60 meters per second. What is the speed of the remaining part? The grenade has a mass of 0.6 kilograms, so let m be equal to 0.6 kilograms. The grenade free falls, reaches a speed of 20 meters per second before exploding. So right before the explosion, the speed of the grenade is 20 meters per second. In terms of the explosion, the initial case is right before the explosion, and the final case is right after the explosion. So initial case, right before the explosion, the speed of the grenade is 20 meters per second. So initial speed of the grenade is 20 meters per second. Right after the explosion, the grenade fragments into three parts. You have M1, M2, and M3. Three equal parts, meaning M1, M2, and M3 are equal. We just divide the total mass of the grenade, 0.6 by 3. We get the mass of each fragment, 0.2 kilograms. The problem tells us that one part flies vertically downward with a speed of 100 meters per second. So let that be M1. M1 flies downwards with a speed of 100 meters per second. So let that be the final speed for fragment 1. V1 is equal to 100 meters per second. The second part flies to the right with a speed of 60 meters per second. Let that be M2. Speed of M2 flies to the right with a speed of 60 meters per second. So M2, we have final speed of M2, V2 is equal to 60 meters per second. We are looking for the speed of the remaining part. We are looking for speed of M3. So we are looking for V3. Now, this is explosion. We use conservation of momentum to analyze the situation. You have initial momentum is equal to final momentum. And again, initial momentum is right before the explosion, and final momentum is right after the explosion. Right before the explosion, there's only one object, the grenade. So for initial momentum, we only have one momentum of the grenade, mv initial. For the final case, final momentum, the object fragments into three parts. So for the final momentum, we have three momenta. Final momentum of fragment 1, you have m1 v1. Final momentum of fragment 2, you have m2 v2. And final momentum of fragment 3, you have m3 v3. So, final momentum of fragment 1 plus final momentum of fragment 2 plus final momentum of fragment 3, you have the final momentum. So, initial momentum is equal to final momentum. This is a vector equation, so we use vector analysis to analyze the equation. We use component method. We have x component and y component. So first, let's have x component. X component of V initial. V initial is vertically downward. No x component. Final velocity V1. Fragment 1, final velocity V1 is vertically downward, so no x component. Next, we have the momentum of fragment 2. So velocity V2. V2 is heading to the right, horizontal, positive direction, so plus M2 V2. Then for fragment 3, we don't know velocity V3. We are looking for the speed of V3. So we simply let V3 be V3x, x component of V3. So we have plus M3 V3x. Isolating V3x, we get V3x is equal to negative M2 V2 divided by M3. We know M2. We know V2, 60 meters per second. We know M3. The equation is complete. We are able to calculate V3x, the x component of V3, negative 60 meters per second. Going now to the y component. So using y component, we have minus mv initial. V initial, the object, the grenade is heading vertically downward. So, vertical, negative direction. So, minus mv initial. Is equal to the final momentum. First fragment, fragment 1, M1 is vertical, negative direction, and M2 is horizontal, no Y component. So we get minus M1 V1 plus 0. And for V3, again, we don't know V3. We are looking for V3. So for the Y component, we simply put V3Y. So plus M3 V3Y. Isolating V3Y, we get M1 V1 minus M1 MV initial divided by M3. Plotting in the known values, we see that the equation is complete. We are able to calculate the Y component of V3. V3Y is just equal to 40 meters per second. Knowing the X component of V3 and the Y component of V3, we are able to calculate the magnitude of V3 by using Pythagorean theorem. So V3 is equal to square root of V3x squared plus V3y squared. Plotting in the values for the X and Y component of V3, we are able to calculate the magnitude of V3, 72.11102,551 meters per second. This is the magnitude of the velocity of particle 3, M3. This is the speed of the third particle, third part or third fragment, M3. So final answer, the speed of M3 after the explosion is 72.111 meters per second. And that's it for our discussion on impulse and momentum. So thank you for watching.